Hi everyone. In this last video, we are going to complete the proof of expansion of the LPS construction. Initially, I wanted to have two more videos on top of that, one beforehand for proving some proposition that I'm just going to use. Actually, it's quite easy, so maybe we don't want to get a full video on that. And the second is how can one proceed and prove the Ramanujanness, like the right bound for this optimal bound for this construction. But this is a kind of a huge story. So what I'm going to do is to spend a couple of minutes at the end of this talk and talk about it a little bit. So this is going to be the last video, and we are going to prove expansion of the LPS construction. So last time we stopped at this point, right? We proved that SQ of PM, how many solutions do you have to this quadratic form Q is related to the right-hand side, which was essentially the spectral side of the non-backtracking random walks that we analyzed. And we said that in order to prove that the graph X is Ramanujan, we need to prove that, so here you have the usual real line where the eigenvalue lives, and we constructed this set theta P, which consisted of these three segments. And this segment, the real segment, this is the complex plane, so this is part of the real line, is bijected with this Ramanujan interval. And these two work bijected with the things outside of the Ramanujan interval. And in order to prove that the graph is Ramanujan, what you need to do, well, you need to show all eigenvalues sits here, except for the trivial one, which corresponds in the theta P picture to show that none of the eigenvalues or the pre-images under this bijection sits here, so they're all real. And that is true, and I'll talk about how to prove it later on. Hint on how the proof goes, more or less, at a very high level. But generally, what we are going to do is we are going to bound the complex part, the imaginary part, sorry, of all of the eigenvalues except for this one. So the reality is that they all sit here, but we are going to show that they maybe sit somewhere here. Okay. And the bound will be depending only on P, and so that you will get some bound, which depends only on the degree, so you get some expansion, some non-trivial spectral gap. Okay, so let's start. So this is the proposition I was referring to when I said that maybe it does require another video, but depending on what you know, for those who actually attended the seminar, that's going to be not too difficult. So just as a reminder, say you have a Cayley graph on some group G with some generating set S, and A is the corresponding adjacency matrix. Then first of all, A can be written like that as an operator. An operator on LG, on CG, on the group algebra, can be written as the sum where you sum over all elements in the generating set, and you apply the regular left or right, depending on what you're doing. This is the left one representation. Okay, I mean, that's what we kind of said in the seminar. We said that really the adjacency matrix is essentially a convolution, and this is one way to describe it. So that's essentially by definition. And the second thing, which maybe requires a little bit more work, but it's also kind of straightforward, is that if you are going to take an eigenvalue of the adjacency matrix and you're going to consider the eigenspace of that eigenvalue, then this eigenspace is invariant subspace of rho. So this is rho G or lambda G, depending on what you're doing. Rho G is the left, and lambda G is the right representation, regular representations. So what I'm saying here is that the eigenspaces of the adjacency matrix are invariant subspaces of the regular representations. So let's take it as is. Good. So from that, you can immediately get the following corollary proposition, that tells you that if mu is a non-trivial eigenvalue of our particular LPS graph, then it has multiplicity which is at least q minus 1 over 2. So it has a very high multiplicity. Every non-trivial eigenvalue, because of the symmetries, appear with high multiplicity. And this is immediate. I wrote the proof here, but this is immediate because there is this correspondence between the eigen spaces of the ingestion symmetrics and the invariant subspaces of the regular representations. And in the seminar, I don't remember if, in the seminar, I don't remember if I did it in these videos, but in the seminar, we worked hard to prove that the non-trivial irreducible representations have high degree, which corresponds to high dimensional eigenspaces. Okay, so that's something that worth recalling. Every eigen, that's kind of the point, one of the points here in Cayley graphs, in particular in this one. Every eigenvalue appears in a lot of time. The larger the irreducible components of the groups or the regular representation of the groups are, the higher the multiplicity is. Good. So with this, we are ready to prove finally the main theorem of the course, which tells you that for any epsilon larger than 0, you want to take epsilon to equal 0 really, but for any epsilon larger than 0, and for every pq as above. So p is a square modulo q, it's 1 modulo 4, q is large enough, and I think that's it. Every non-trivial eigenvalue of the LPS graph X is bounded not by 2 square root of p. I mean, it does, but the theorem doesn't say 2 square root of p as we want. It gives you this bound. This is kind of negligible, but it gives you this bound of p to the 5/6 plus epsilon for any epsilon that you would want. Okay, so the 5/6 gives you a spectral gap, a polynomial spectral gap from p. P is trivial, p to the 5/6 is non-trivial, but like, for example, the zigzag product gets you like p to the 3/4, if you know what that is, or slightly even better. Well, let's say the 3/4. But we want a half, and that's not a half, but that's a very non-trivial bound. And as we will see, there is the proof for homogeneous proceeds with the exact same lines as we did for the course and for our disproof, except for one place which I'm going to talk about later. So this is where we kind of cash out from this game. Okay, so let's prove that. So kind of connected to what I said at the beginning, recall that SQ of PM is this expression, where the theta j's are those pre-images under this map. The mu's sits here, the theta's sits here. Okay. And now, if you have kind of by a kind of contradiction, or not really contradiction, but if you have some eigenvalue which doesn't sit in the Ramanujan interval, a non-trivial eigenvalue, but doesn't sit in the Ramanujan interval, so it has a complex part, an imaginary part, right? It's in this picture. It doesn't sit here, it sits somewhere either here or here. So it has a non-trivial kind of imaginary part. So let's denote that imaginary part by psi of j. Right, so you can write theta j as either I times psi j if you sit at this right bit of these three segments, or maybe it's pi plus I psi j because maybe you sit at the second, maybe you sit here. So the real part is either 0 or pi, but there is an imaginary part between 0 and ln square root of p. Right, so psi j is this number between, so psi j is always between 0, we assume it's strictly larger, and up to ln of square root of p. Okay, so we want to bound psi j really, and from there we're going to remind ourselves how we bound mu also, but really, that's the point. So to do that, we are going to use the hyperbolic sine and cosine function. So I'm just going to call them sine h and cosine h. But so remember that sine h is can be written as e to the z minus e to the minus z over 2. You can write everything in terms of exponentials, and the hyperbolic cosine function is this thing. And now, for any j such that mu j doesn't sit at the Ramanujan interval, let's consider this ratio because it appears here. Okay, so let's consider this summand corresponding to psi j. So you can write it as because just because theta j is either I psi j, this is this part, or maybe plus a pi, because of maybe you're in the other bit of these three segments, then anyhow you can express it as just instead of writing the theta j's, you can just write I pi j, right? The additional pi which can potentially happen doesn't change anything because you have it in also you have it both in the numerator and the denominator. So right, if it negates, that it negates both. And this is precisely this ratio of the hyperbolic signs, right? Because the minus, again, doesn't change anything because it appears both in the numerator and denominator, and the I cancels out. Now, this function is positive, so this is a non-negative thing. The hyperbolic sign looks like something like this. And everything here is positive. Psi j is positive and n plus 1 is positive. So in the positive side. Good. Now let's say that we are going to fix one particular eigenvalue which doesn't sit, non-trivial eigenvalue which doesn't sit in the Ramanujan interval. So k is going to be the corresponding index. So let's write SQ of PM as follows. So first of all, we are going to, so SQPM has this 2 over n p to the m over 2 factor, but then you sum up over all eigenvalues, this ratio between sine n plus 1, theta j, and sine theta j. So we are going to take out the kth element, all eigenvalues that has the same magnitude as mu k. And remember, we denoted the multiplicity of mu k by this m of mu k, which we know is large. That's going to play a role at the end. But let's take all of the summands that has the same value, maybe different index, but same value as mu k. There are m of mu k of those, and each contributes this thing, right? Where I used the psi k notation with the hyperbolic sinuses rather than the thetas. And then also there are the remaining contribution of the remaining summands, which again, I'm going over all j's for mu j is not mu k. I'm keeping the signs and don't go to hyperbolic signs here. And the point is that if you know what the trace method is, then this is kind of resemble to that in a sense. You take one big potentially eigenvalue and kind of bound the remaining contribution of the remaining eigenvalues. But here you make an extensive use of the fact that this eigenvalue, which is big, comes up with a bunch of eigenvalues which is as big. Okay, but anyhow, the remaining eigenvalues, those that are here, if you look at this ratio, then, first of all, we can bound this from below. Everything here is positive, right? Because if theta j is because the signs of the sinus at the numerator and the denominator will make sure it's positive. So I can, to bound this from below, first of all, I'm only going to take a subset of the indexes over which I sum. So I'm only going to take those j's for which the absolute value of mu j is at most 2 square root of p, namely only eigenvalues that sit in the Ramanujan interval. And For each of those, I'm going to notice that this ratio of signs is bounded by n+1. Okay, that's an easy kind of calculus thingy. That's because sin x over x approaches 1 from the right direction here, and so you can show that easily. So this means that SQPM can be bounded from below as well. You have this expression, this term, which appears here, the one coming from the kth large non-trivial eigenvalue, and then all of the remaining ones may subtract at most. This is a low bound. At most, well, according to this bound, that we have 2 to the p m over 2 times n+1, right? Because you have at most n summons here, so this cancels out in the right direction. And then this is the 2 p m over 2 that you have here, and each of the summons here is at most n+1. Is at least n+1. Okay. Good. So we bounded from below SQ of PM. And note that in this bound we have the multiplicity, kind of stressing that again, we have the multiplicity of this bed or any non-trivial eigenvalue. And that's useful because the bigger it is, the bigger the lower bound is, right? And M, I didn't say that, but M is a parameter that we are going to choose later on. So think of M as some parameter now for the moment. Right, so to summarize, we are here. And this is the bound that's actually also used in the Ramanujan proof. The difference is in the upper bound. So we are going to bound SQ of PM from above now, and that's going to be like kind of by hand, maybe slightly weird bound. And the actual bound is actually can be obtained, the right bound, like a bound with the right error term asymptotically, can be obtained using deep results, which I'll talk about. But what I'm saying is this is the first time that we split from the original proof and just prove something, prove the expansion rather than Ramanujan. Anyhow, so we want to bound this from above now. And recall, SQ of PM is how many integral solutions you have to this equation, which is, we call it Q or Q prime at this point because of the 4 that appears there. Let's do this equation. And now let's bound how many solutions are there kind of in a kind of almost trivial way, okay? So first of all, x0, let's look at x0. It's kind of different than the rest. So it's at most p to the m over 2, because I mean, this happens and these are positive. So in absolute value, it's bounded by p to the m over 2. And so this means that modulo q squared, in addition to that, looking at this equation and taking modulo q squared, you see that x0 squared is p to the m, modulo q squared, because this is 0. And from these two, you can immediately see that x0 is plus minus p to the m modulo q squared. Right, it's an easy exercise. If a squared equals b squared modulo something, then it's plus minus the b. Right. And actually, because x0 and p are odd, you can improve that, and this equality holds modulo 2q squared because they have the same parity. So anyhow, this is just to say that there are at most p to the m over 2 over q squared, plus 1 just in case, or take a flow setting and so forth. Possible solutions for x squared. Right, because in every q squared interval, it has to be equal p to the m over 2. Right, so x0, the number of potential solution. So every solution, x0, in every solution, x0 can obtain one of these values, one of these many values. So now let's fix x0, and now we are left with solving this equation, which is more symmetric. So how many, essentially, if you think of this as some number n, how many ways do you have to write n as a sum of free squares, integral squares, right? And at the beginning of the seminar, we talked about how many ways are there to write a number n as a sum of two squares, and that's allowed us to look at the Gaussian integers, because every such a solution is coming from a Gaussian integer, and the solution, it being like the a squared plus b squared equal n, means that these Gaussian integers as a norm n. And much like that, when we talked about how many ways are there to write n as a sum of four squares, when the corresponding algebraic structure was the quaternions, which are very useful here, right? We did the Gaussian integers as a also for this, but as a warm-up for the quaternions. Because this is a commutative ring, this is a non-commutative ring, it was more difficult. But anyhow, during that, we proved that the number of solutions in the two cases, so R2 of n, how many integral solutions are there, like a and b are there, such that a squared plus b squared equals a given n, is given by this very nice formula. It's 4 times d1 of n minus d3 of n, where d1 of n is how many divisors of n do you have, which are equal to 1 modulo 4. And d3 is the same, but with 3 modulo 4. It's a very, very elegant formula. And from this, using a kind of a very simple, kind of similar to what we just did now to remove x0 kind of argument, we can bound at least R3 of n. So how many solutions do you have there? Well, it's something like it's bounded by something like square root of n. Okay, it's for any constant epsilon that you would want, you'll get some function of this constant, c of epsilon, times n to the half plus epsilon. Okay, so this is the shorthand notation for that. Okay, good. So that's what we need. We need this bound on how many ways are there to write this n as a sum of three squared and three squares, and the answer is the square root of the number, essentially. Right, so let's apply it here. So R3 of this number is, and I'm also going to give up this part. I don't care about x0 squared, like getting something out of it, I won't. So removing this part, so this is bounded by essentially the square of this thing, which is what's written here. There is always this epsilon that's floating around, just to make sure that we are not saying something which is incorrect. But you should really think of epsilon as kind of very small, or even zero, at the first look. Okay. So with this, we can bound from above SQ of P of M, right? We need to multiply how many ways are there to choose x0 times this bound that we got after we fixed x0. Right, so this is the bound that we just got. And this is the bound that we had on how many options x0 have. And if you multiply these two and do very, very, very simple calculation, you get to this slightly cleaner bound, in which you have these two summands, p to the m times 1 plus epsilon over q cubed. Okay, the q cubed comes from this q and this q squared. It's a real thing. You have a q cubed there. And when the second term is like p to the m over 2 over q. These are currently incomparable. Good, so we bounded from above SQ of P of M. So if you go back, before we bounded from below SQ of P of M by this expression, and now we just bounded it by this other expression that uses this R3 bound. So using these two bounds, kind of ignoring SQ of P of M, which was just a useful tool for us, we get this bound now. We get this lower bound on SQ is smaller than this upper bound on SQ. Okay, actually, this, if you remember, was here with a minus, but I just moved it to the other side. Okay, so let's clean this up a little bit. So first of all, n, the number of vertices of the Cayley graph, is bounded by q cubed. We have an exact formula, but let's just replace it by q cubed. I mean, in the right direction, we're going to replace this n by q cubed. And also we are going to divide by q cubed. n by, so we are going to multiply by q cubed to clean this up, and divide by p of m over 2, whatever it does. So if you do that, then what you get is that this thing, which is here, because you multiply it by q cubed, which is n, and divide by this, okay, is bounded from above by this expression. Right, so this is that because you multiply by q cubed and divide by that. And this is also the case. I mean, this is, this thing is that because you multiply by q cubed and divide by p to the m over 2, so you have this half now. And here you multiply by q cubed, so you got a q squared, and divide by p to the m over 2, so this one goes away, and you have this. The 2 cancels. Okay, yeah. Just stare at it for a second. It's very simple. And now we're actually going to finally choose m. We are going to choose it such that this holds, so p to the m over 2 is bounded by q cubed, but you should think of it as we choose it as the maximum m for which this holds. And the best way to think about it is just that m is satisfying that with equality, even though that doesn't make any sense because you can't have equality. This is a power of 2 different primes, but asymptotically you should think of it like that. Here in the equations, I don't think of it like that, but that's what you should do. So if you choose such m, then you can replace essentially every p to the m over 2 with q cubed. So for example, this p to the m over 2 becomes this q cubed. Right, this stays the same. So this p to the m over 2 becomes this q cubed, and this p to the m becomes q to the 6. And also this m becomes essentially log to the base p of q times 6 because of the 2 times 3, and maybe plus 1 because you can't have exact equality, or maybe actually it's just this one. And what I just said is fine because this is the right side of the inequality. Yeah. Okay, so you get a slightly nicer inequality. And yeah, okay. So I think I copied it here. 1 second. Yeah. So this is where we stopped. And I should go here. So I copied it here. And now what I want to do is I want to remove this thing. So recall that psi k is at most ln of square root of p. It's between 0 and ln of square root of p. It's the imaginary part of the preimage of the eigenvalue. And the sine function generally, the hyperbolic sine function is e to the z plus or minus e to the minus z over 2. I forgot. It doesn't matter for what I'm going to say, but it's with a minus. So even better. And this is bounded by e to the z, right? So even less than that. By e to the z. And so if I want to bound the hyperbolic sine of psi k, it's at most e to the psi k, and psi k is at most ln square root of p, so this is no square root of p. And so again, this is the right direction in terms of these inequalities here. So I can replace this with a square root of p, and then multiply it by that. And this way I'm getting this nicer inequality, which takes this part, this bit here. That's what you have here. And this is bounded by this expression, like cleaner expression. So how did you get to that? So first of all, this is, you can remove that and multiply this constant by a factor of 2 or less. And yeah, and also essentially all of this, because here you have q cubed, which wins that. And this thing is, for q large enough, it's smaller than q to the epsilon. If you take the q large enough, if you fix epsilon and take q large enough with respect to p, then you can also ignore that by multiplying by another factor of 2 or something. Okay, and the square root of P also gets swallowed by that. I mean, if Q is large enough, again, that's the same thing. Right. Yeah, so all in all, you get that this is the only really meaningful term in the bound. And so finally, we get this bound, which I wrote here, which is the multiplicity of this eigenvalue times the hyperbolic sign of m plus 1 times psi of q is bounded by this. Okay, and as I said, we are going to choose m the largest possible for which this holds. And when you do that for q large enough, what you'll get, so I really want now to bound this from below, so that I'm only going to be left with this expression, bound on this expression, another bound on that expression. Right, bounding this from below will give me an upper bound on that, because I have an upper bound on that. Right, so this hyperbolic sign of m plus 1 times psi of k, right, so as I said before, the hyperbolic sign is easy minus e to the minus z over 2. Before we used an above bound, but now we're going to use a lower bound, which is, say, e to the z over 3. I mean, because this is smaller than that. When z is at least 0.5 something, but let's say when z is at least 1, that's the case. You need to go away from 0 a little bit, but after that, then you're fine. So this hyperbolic sine function of m plus 1 times psi k is this e to the m plus 1 psi k over 3, and plugging in the bound that we have, plugging in, so because we choose m the largest possible value for which this holds, we know that m is sufficiently large, and so you have this inequality where I can replace m by this expression. And then just messing around a little bit with what you see, you get this p to the minus 1/2 over 3, because psi k is bounded by ln of square root of p, times whatever you see here, e to the 6 ln to the base p of q times psi k. Good. So I copied the two bounds that we had. We have this and we have that. I mean, we have an upper bound, an upper bound on this, and we just get a lower bound, this one, on that. So we are going to get an upper bound on m, on the multiplicity of mu k. All right, so, and the upper bound is going to be this thing. All right, I'm just this divided by that. If you clean it a little bit, you see you have this expression, this q to the 3 plus 6 epsilon, and then at the exponent you subtract these things, because this doesn't matter. It goes to the O of epsilon. But on the other end, and that's the crucial point, we know that the multiplicity of mu k is huge. It's a non-trivial eigenvalue, so it's at least q minus 1 over 2. And so this means that, now ignoring this multiplicity now, you have this thing. So you have this something which is linear in q, which is bounded by above by something which is, q to the some number times constants. But as q gets large, in order for that to way that can happen, this exponent of q is at least 1. Right? I mean, those constants won't save you as you increase q. And so we get this inequality, right? This exponent here is at least 1, so that it will be able to win this q. And moving things around, the 1 goes here, and you divide by 6 and multiply by ln p, you get finally a bound on the imaginary part of mu k. Namely, psi of k is bounded by 1/3. That's because this 3 minus 1 becomes a 2, and then you divide by 6. 1/3 plus epsilon times ln p. And that essentially gives you a bound on mu, but let's just do that. But finally, we're able to bound the imaginary part of these, potentially existing eigenvalue that sits outside of the Ramanujan interval. It can't sit too far from the Ramanujan interval. in the pre-image when you look at these three bits. It has to sit somewhere here. So let's do that more concretely. Let's actually bound mu k. We're using the fact that we know a bound on psi k. So we know that theta k is either I psi k or I psi k plus pi, depending on whether you sit here or here. And we know that mu k, like that's the bijection that we have between the thetas and the mu's, is 2 square root of p times cosine of theta k. And so taking absolute values, then the absolute value of mu k is 2 square root of p times the absolute value of cosine of psi k. Now psi k, theta k. And theta k is I psi k, maybe plus pi, but the cosine doesn't care. This absolute value doesn't care about the pi. So you can just write it as cosine of I psi k. And remember that the hyperbolic cosine is exactly I times cosine of I, or maybe with some minus there, but yeah. No I. So the hyperbolic cosine is exactly cosine of minus IZ. I never remember those. So the absolute value, you have a minus here, it doesn't matter for cosine, so it goes away. And then you get this bound of 2 square root of p times cosine hyperbolic cosine of psi k. So to recap, we just proved this, that the absolute value of mu k is bounded by this 2 square root of p hyperbolic cosine of psi k. And before, we bounded this psi k, which is the imaginary part of mu k, of theta k. Sorry, after you move back to these three intervals, is bounded from above by 1/4 plus epsilon times ln p. And so the hyperbolic cosine, which appear here, which is applied to that, well, that's e to the z plus e to the minus z over 2. And our z is this thing, or this is a bound on this thing, and this is a monotone. So plugging this in, you get this p to the 1/3 plus epsilon plus p to the negation of that, which is small and we don't care about it, but it's there, over 2. And then plug in this, like multiplying by 2 square root of p, we finally get what we wanted to prove. That the absolute value of mu k is bounded by p to the 5/6 coming from here, plus epsilon plus something which you kind of should ignore, but it is there. So it's not true that it's 1 times that. It is true, but it's not true in this proof. Plus this little error term, but this is the main part. Good, so that really completes the seminar. And but I do want to say a few words about how do you get the Ramanujan bound? Like, what's the difference between what we just did and what you should do in order to get the Ramanujan bound? So actually, everything we did is used, except for, as I said, except for the last step in which we gave an upper bound on SQPM. And you saw this upper bound was kind of by hand, and it's kind of clear that it's not tight. I don't know, it doesn't look as it is tight. And it turns out that the correct bound, and actually copying it from the book, and I haven't checked, but the correct bound is this thing. So you have this expression, which looks like very specific, plus an error term. And it turns out that this very specific looking expression, which is not part of the error term, actually precisely captures the trivial eigenvalue. So it's there for the right reason. That's the thing you should aim for. If you do the calculation going back and forth between theta p and the interval, the real interval where the eigenvalue live, where the eigenvalues live. And a similar analysis to what we did, if you know this bound, will give you the Ramanujaness. That's not hard. It's like half a page in the book. It's an exercise. But the question is, how do you get this bound, this upper bound, rather than the bound that we got? And that's deep. So it turns out that in order to prove this bound, what you need to do is to do the following. So let's consider this theta of z function. So you sum over all 4 tuples, 4 tuples, and you evaluate this Fourier-looking expression this is a function of z. But if we look in expression where this thing is the q prime of x, that's the expression that we had for defining SQ of PM. Another way of writing it, which is nicer, is to go over all integers k, positive integers, and to have this coefficient in front of this Fourier term. And RQ prime of k is how many integral representations of k do you have by q prime. This is the thing that we had when we defined SQ of p of m. And the point about this function is that it turns out, I mean, it doesn't seem like that. This is kind of the Fourier representation of it. But it turns out that this is an extremely symmetric function. It's a modular form of weight 2 in this case. So what are modular forms? That's an entire subject, but essentially it's a function with extreme amount of symmetries. So you should think of function of the in the complex plane of a positive part of the complex plane. Denoted like that. So the imaginary is larger than 0, and it's a function that satisfies this thing. So if you apply theta to any z in the upper half part of the complex plane, but you don't apply it to z, you apply it to this Mobius transformation applied to z, where the corresponding matrix come from SL2z. That's no coincidence that our construction looks at SL2 Qs and so forth. Then it satisfies, well, it is f of z, so it's kind of symmetric, but there is this kind of initially weirdly looking factor of cz plus d to the k. K is the weight. So it turns out, and it's not clear by looking at it, that this function satisfies that with k equals 2. Okay. And it turns out that these modular forms have a deep connection with elliptic curves. So in particular, the coefficient that we care about, that's what we want to bound. What is for k prime, but when k is not prime, it follows from the prime cases. Then this exactly corresponds to the number of points of the corresponding elliptic curve when you look at it over the finite field FP. So this is part of the much bigger modularity theorem. That's a deep result. I mean, it's not something that you can teach like in one course, I guess. And now on top of that, the number of points in an elliptic curve over a finite field can be very well approximated by the Hasse-Weil bound, which is kind of equally deep to what's going on here, because the Hasse-Weil bound is essentially the proof of the Riemann hypothesis, but not for the usual ring of integers. That's, of course, conjecture. It's an hypothesis, but for function fits. Namely, when you are looking at some algebraic curve and look at the function field and you have these analog of primes and divisors and so forth to that case. So that by itself is a huge topic. It's a fantastic result, and it's also used when you do algebraic geometric codes, and that's why I actually do prove this theorem in complete. There is a complete proof of the theorem in other videos that I have about, of course, about AG codes, algebraic geometric codes. But anyhow, yeah, I think we should stop here. And I do play with the idea of actually giving a course about that. That was a seminar, so the pace was a bit different. In a course, we'll have more time, and we can certainly, like in Tel Aviv University, not a YouTube course, we can certainly say more about modular forms and the relations to elliptic curves, not prove everything, but still have some good insights about it, and maybe potentially prove a weaker Hasse-Weil bound for elliptic curves using Bombery's proof. You can actually prove it, and so you can get a better, maybe not but even better approximation than what we got here. Yeah, anyhow, so I think we should stop here.